Hello viewers, welcome back to my channel Experience Physics. The topic for today's lecture is Wheatstone Bridge. Wheatstone Bridge is a simple arrangement of some resistors, say 5 resistors, which is used to find one unknown resistance, right? First let me draw the diagram of Wheatstone Bridge. This is the diagram. G means it is a galvanometer which is connected between these 2 points, right? These are some resistors, say R1, R2, R3 and R4. This is a simple setup. Right? These 2 terminals will be connected to a battery of V volts. This battery is expected to send one current, right? This current will divide into 2 paths. By choosing the values of R1, R2, R3 and R4, I can make the current through the galvanometer as 0, right? The galvanometer is used to detect any current between the points, not to measure any current, right? It is like an ammeter. The galvanometer can detect even small amount of currents. Small amount of currents they detect, galvanometer. Say microamperes. Even such a small amount of current, they will show its deflection, right? That is why we are connecting a galvanometer between the 2 points. Let me mark the points as A, B, C, D. I can make the current through the galvanometer by adjusting the values of R1, R2, R3 and R4. The condition is to have Ig is equal to 0 or the potential at the point C is equal to the potential at the point D, or Vc is equal to Vd, so that no potential drop is available between the 2 points C and D. If Vc and Vd are having the same potential, no potential difference. If there is no potential difference, then there won't be any current through this branch, right? Usually galvanometer will have some resistance, low value of resistance galvanometer, right? Galvanometer, inside the galvanometer some resistance is available, right? It is not an ideal meter which is having infinity resistance. It will have some low resistance, right? So it will carry some current also in practical cases, but I can choose the values R1, R2, R3 and R4 such that I can make Vc is equal to Vd. What is the condition? The condition is R1 by R2 is equal to R3 by R4. This is the condition. R1 by R2 is equal to R3 by R4. If it is chosen, if this condition is met, then Vc is equal to Vd. Then if R1 by R2 is equal to R3 by R4, then Vc is equal to Vd. If Vc is equal to Vd, galvanometer, the current through galvanometer is 0, right? Ig is equal to 0. The galvanometer won't show any deflection. It won't deflect. The pointer will be standing on the middle position, right? The galvanometer can show the positive deflection as well as negative deflection, right? So this is Wheatstone Bridge. The Wheatstone Bridge, it is published by the work of one scientist, Charles Wheatstone, a British scientist, Charles Wheatstone, and it is named after his name, a British scientist, right? Okay. R1, R2, R3, R4 must be put such that R1 by R2 is equal to R3 by R4. That's all, right? We will see the proof. A, B, C, D. Let me connect a battery here. It will send one current. I have not connected the galvanometer. Time being, let us not connect a galvanometer, right? So this current will divide as I1 and I2, two branches. Say this is R1 and R2, R3 and R4. The current entering here and leaving here. This current enters here, leaves here. Enters here, leaves here. This current enters here, leaves here. Then the drop across this R1 is equal to I1 R1. I1 R1. Ohm's law. This is I1 R3. This is I2 R2. This is I2 R4. These are the voltage drops, right? So I want to make, this is VA. The potential here is VA. The potential here is VD. The potential here is VB. And the potential here is VC. VA, VC, VB, VD. These are the potential at the points. Right. I want to have the potential of C and D to be equal. So I assume VC is equal to VD. I want to prove VC is equal to VD by having the values R1 and R2. The combination of values are such that it is going to be achieved. VC is equal to VD, right? First let us write what is VA minus VC. VA minus VC. Equation number 1, VA minus VC. VA minus VC is equal to I1 R1. Then VA minus VD is equal to I2 R2. This drop, VA minus VD. What we have assumed? VC is equal to VD. So I can replace this VD as VC. So this equation will also be VA minus VC. This substitution I can make because I have assumed already VC is equal to VD. So I am writing VD is equal to VC. VC minus VC is equal to I2 R2. VA minus VC I1 R1. VA minus VC I2 R2. By comparing these two equations, we can write I1 R1 is equal to I2 R2. This is for this part. Then come here. VC minus VB, because the current direction is this way. This way it is flowing, the current. From here, left to right. So VC minus VB is equal to I1 R3. VC minus VB is equal to I1 R3. Similarly, VD minus VB is equal to I2 R4. I2 R4. According to the assumption VC is equal to VD, I can make this VD is equal to VC. Then VC minus VB, VC minus VB. So I1 R1, I1 R3 is equal to I2 R4. By comparing these two equations, we can write this one I1 R3 is equal to I2 R4. Right. Now here I am finding this ratio R1 by R2 is equal to I2 by I1. Now replace I2 by R1 by the resistor. I2 by R1 from here we will find I2 by I1 is equal to R3 by R4. Put this I2 R1 here. R1 by R2 is equal to, instead of I2 by I1 I can write R3 by R4. If this is true, this will also be true. This is one assumption we have made in the beginning. VC is equal to VD. If VC is equal to VD, if this assumption is true, R1 by R2 is equal to R3 by R4, right? Otherwise, to achieve this VC is equal to VD, you must make the ratio R1 by R2 is equal to R3 by R4, right? Now, I have chosen the values R1 by R2 is equal to R3 by R4. Say R1 is equal to 10 ohms, this is 2 ohms, and this is 20 ohms, R3 divided by 4 ohms. So this R1 is equal to 10, R2, just let us assume with some numerical values. R1 is equal to 10, R2 2, R3 20, R4 4. 10 by 2 5, 20 by 4 5. So this is true. If I have such values, these two voltages will be same. So no matter what is the value of this resistance which will be connected between C and D, it won't affect this voltage, right? If I have one galvanometer, it won't show any deflection. If it is an ammeter, instead of this resistance here, let me connect one ammeter, the I value will be 0. If it is a galvanometer, it won't show any deflection. If it is a resistance, it won't carry any current, right? If it is achieved, this can also be possible. So no matter the value of resistance which is connected here, right, the current will be 0. The center arm, always the current through it is 0, right? Then what is the use of this Wheatstone bridge? Application or use. What is the use of it? This is the setup. R1 by R2 is equal to R3 by R4. Okay, we can make. Then these two voltages will be same. No current will be flowing through it. What is the purpose of making this arrangement? Right. To determine the usage of Wheatstone bridge is to determine any unknown resistance. If you have one conductor, its resistance value, if you want to know, you can make this setup, you can find the value of this unknown value of that particular conductor resistance. So determine any unknown resistance value. R1 is equal to known. This R1 is known and fixed. This R2 is also known and fixed, constant value. This R3 is equal to known but not fixed. This is a variable one. R3 can be varied, right? But it's known value. R4 is unknown value. If you make this setup and you give any value of battery voltage source here, right? You adjust the values of this variable resistance, because this is fixed, this is unknown value, but we can't make any changes here. We can make changes in this resistor only, because it is a variable one. You are varying the value such that the current through the galvanometer is 0, right? You are looking for any deflection is there, right? If there is no deflection, you will stop at that particular value. This is usually a resistance box. a resistance box, a lot of knobs will be there. You are rotating the knobs and you are fixing the value 1 ohm, 1.5 ohm, 1.2 ohm, 1.3 ohms. Similarly, this way, like an eye doctor which is putting the lenses to find the power of your lens. Similarly, different resistance are put here, connected here, and finally it will be achieved when R1 by R2 is equal to R3 by R4. Right? This is fixed and this is varied and this is unknown value. Then you are writing this formula and you are finding what is the value of that conductor R4, unknown value, right? So this is the usage of one Wheatstone bridge. To find the value of one unknown resistance, we will use this Wheatstone bridge and we will make this setup. So let us solve some numericals. The first one is the effective resistance between A and B is. So this is also Wheatstone bridge. If you redraw it, you will come to know that this setup is a Wheatstone bridge, right? A, B, right? These two nodes, let us say C and D. I am redrawing it. A, B, and this is C, and this is D. Between A and C, 2 ohms. Between A and D, 1 ohm. Between C and D, 5 ohms. Between C and B, 4 ohms. Between D and B, 2 ohms. Okay, this is A and this is B. The question is the effective resistance only, right? The effective resistance only. We are first checking whether it is a balanced or unbalanced bridge. If R1 by R2 is equal to R3 by R4 and the potential between the center branch, potential drop across the central branch is equal to 0, we say it is a balanced Wheatstone bridge. If it is achieved, this is known as balanced Wheatstone bridge. In that condition, the potential between the 2 points is same, no current is flowing through the center branch, so you can exclude, you can remove that particular resistance. No matter how much value is connected between C and D, it won't carry any current, so technically it is absent, you can remove it from the picture, right? So 2 by 1, R1 by R2, 2 by 1 in the left hand side, 4 by 2. Yes, it is a balance. 2 is equal to 2. It is a balanced Wheatstone bridge. So now I can remove this particular resistance. I can remove. Since it is a balanced bridge, I am removing it. Now 2 and 4 are in series. 1 and 2 are in series. These two are coming in parallel. So 2 plus 4, 6. 1 plus 2, 3. 6 and 3 are in parallel. 2 plus 4, 1 plus 2. 6 and 3 are in parallel. 6 into 3 divided by 6 plus 3. That is the equivalent value. 9. 2 ohm is the answer for this circuit. 2 ohms. Option A. Next problem. If each resistor of the network has resistance R, all are R, then the equivalent resistance between A and B is what? This is also Wheatstone bridge arrangement. The other two nodes are C and D, right? Time being, you forget about this bottom resistance. And if you redraw it, you will know this is a Wheatstone bridge. AC, AD, CB, CD. This is the center branch, right? You forget it, and if you analyze the circuit, you will come to know that it's a Wheatstone bridge. Then the current through the center part will not be, will be 0. The current through the center part. This resistance will not be used here, right? Balanced one, R by R, R by R. Equal values, so R by R, balanced Wheatstone. This you will remove this part between C and D. This R and R, series, this R and R series, 2R are parallel, R is the result. Let me draw it. R, another R, this is D, R, this is C, then this is the bottom R, the last one. This point is D, this point is C. So 2R and 2R, this is the equivalent value. 2R, R. So 1 by RAB is equal to 1 by 2R plus 1 by 2R plus 1 by R. Then I am taking 2R LCM, 1 plus 1 plus 2, that is 4 by 2R, that is 2 by R. Then RAB is equal to inverse R by 2. R by 2 of R, option D is the answer. Right. So 1, 2, 3, 4, 5. These resistors, these arrangement make a Wheatstone bridge. Then finally you are connecting this one between A and B. Between A and B, any number of resistors you can connect. Any number of resistors. You need not wait for 5 resistors or 6 resistors or 7 resistors. This arrangement must have 5 resistors. Right? The 6th arrangement may come between A and B. The 7th resistance may come between A and B. The 8th resistance may come between A and B. This way you can add any number of resistors. Right? Okay. The same problem can also be solved by mirror symmetry. If you find equal number of values, R, you look for solving the method using methods of symmetry. Methods of symmetry. It is a symmetry arrangement. So, 2 methods we have studied: mirror symmetry and folding symmetry. For methods of symmetry, a separate video has been made and its link is available in the description box. You please check it and you watch that video also. For mirror symmetry and folding symmetry, this problem cannot be solved using folding symmetry. This problem can be solved by mirror symmetry, right? Next problem. A circuit consisting of 5 resistors, each of resistance R, forming a Wheatstone bridge. What is the equivalent resistance of the circuit? So immediately you can write the answer. The values are equal values consisting of 5 resistance and all the arms are having equal values. The answer will be that same value. R and R. So balanced one. So the 5th resistors is removed. 2R and 2R are parallel. Then R will be the answer. Option B. For Wheatstone bridge, if all the arms or all the branches are having same value, that value will be the answer. If it is R is the answer. The following circuit consisting of 5 identical resistors, each of resistance R. 1, 2, 3, 4, 5. The equivalent resistance between A and B is, if you redraw it, you will come to know this is also a Wheatstone bridge, right? You take B here. B. From B to this point, so this is A. This is A, this is B, this is C, and this is D. I am going to draw B here. Then B to D R, this is removed. Then B to C, this is another R, this is removed. Then if you look at it, this is A, this part is removed. This part is removed and it is brought here. A, B, C, D. 1, 2, 3, 4, 5. It's a Wheatstone bridge. This is the center arm. RR. Balanced one, no current, 0 ampere is flowing. So this can be removed. So already they have mentioned it is consisting of 5 identical resistance, right? R. So the answer will also be R. Option D. The current I drawn from 5 voltage sources. So find R equivalent and you find I. V divided by R equivalent. Voltage is given. So the first step is to find the R equivalent. This is A and let it be B, and this is C and this is D. Let us redraw it. A, B and C, D. A and C 5 ohms. C and D 10 ohms. A and D 10 ohms. D and B 20 ohms. Then C and B 10 ohms. Yes. All the 5 resistors have been drawn here. Then between A and B 5 voltage. 5 voltage. So to find this current I, we need the R equivalent. 5 divided by 10, 1 by 2, 10 divided by 20, 1 by 2, balanced. So this particular resistance can be easily removed. Then 5 plus 10, 15, 10 plus 20, 30. 5 plus 10, 15 is parallel with 30. These two arms are in parallel. R equivalent is 15 into 30 divided by 15 plus 30. 450 divided by 45. 10 ohms. R equivalent is 10 ohms. Then V divided by R equivalent. I is equal to V divided by R equivalent. 5 is the source value, 10. So 0.5 amperes. 1 by 2, 0.5 amperes. Option B is the correct answer. Next, the Wheatstone bridge is shown in figure is, the Wheatstone bridge shown in figure is balanced. If the positions of the cell C and the galvanometer G are interchanged, G will show 0 deflection when. So this is Wheatstone bridge, balanced one. Already it is a balanced one. That means R1 by R4 is equal to R2 by R3. So it is not showing any deflection, balanced one. Now we are interchanging C and G. Between these 2 points we are connecting the battery, between these 2 points we are connecting the galvanometer. What would be the options given? In all cases, only if all resistances are equal, only if R1 is equal to R3 and R2 is equal to R4. Option B, if all are equal. Option C, R1 equal to R3, R4 is equal to R2. Only if R1 by R3 and R2 by R4. Let us find which one of the given 4 options is correct. So this is balanced one. For this first case, let us write the balanced condition. The condition for balance is R1 by R4 is equal to R2 by R3. This is the first condition. Now let us rewrite R1, R2. We have to interchange the positions of the cell and the galvanometer. The cell comes here now. The galvanometer is connected here. R1, their positions are not changed. The resistance are, their values and their positions are not changed. R1, R2, R3, R4, right? Only the cell and the galvanometer positions are changed, right? So now cell has come here. The galvanometer, usually it is the center branch. For balanced condition, we will look for the potential so that the galvanometer carries no current. That means these 2 points must have same potential. These 2 points must have same potential. Right, because this is the place where the galvanometer is connected. So R4 by R3, for this arrangement, we write R4 by R3 is equal to R1 by R2. Right, here R1 by R4 is equal to R2 by R3. If we cross multiply it, I can rewrite this same equation. R1 by R2 is equal to R4 will go up, R4 by R3. What is this one? From here, I am writing R1 by R2 is equal to R4 by R3. Here it is R1 by R2 is equal to R4 by R3. If you compare these two equations, equation first and equation 2, if you compare these two equations, you will come to know that both are same, right? So if it is a balanced Wheatstone bridge, even if you replace the positions of cell and the galvanometer, nothing will change. The balanced network remain balanced, right? So in all cases, option A is correct. It won't affect the setup. In all cases, it is true. If it is a balanced one, it is always a balanced one. Next problem. In Wheatstone bridge, 4 resistors of resistances 15 ohms, 12 ohms, 4 ohms and 10 ohms are connected in cyclic order. In Wheatstone bridge, right, first let us draw the circuit. In Wheatstone bridge, 15 ohms, cyclic order means then I must write 12 ohms here. Then I must write 4 ohms here. Then it is 10 ohms. Cyclic order. The resistance in ohms, that is to be connected in parallel with the resistance of 10 ohms. A resistance is to be connected here. Parallel with the 10 ohms, with the resistance of 10 ohms, to balance the network is, to balance the network, to make the potential at this point to be same, then only it is balanced, right? So 15 divided by its equivalent value must be 12 by 4. Its equivalent value is 10 into R divided by 10 plus R. It is in parallel, connected in parallel. 10R divided by 10 plus R. 15 divided by this value. 15 divided by this value must be equal to 12 by 4. So this is 3. Then this will be 15 into 10 plus R divided by 10R. which is equal to 3. into 10 plus R is equal to 30 R. Then it is 2. So 10 plus R is equal to 2R. So this side it is 2. 10 plus R is equal to 2R. Then 10 is equal to 2R minus R. So R value must be 10 ohms. Option B. So I have to connect one 10 ohms here. So it will be 10 and 10, 5 ohms. 15 by 5 is equal to 3. 12 by 4 is equal to 3. Yes, the answer is correct. In the Wheatstone bridge shown below, the condition to obtain balancing is what? So here R1 is equal to 3 ohms and R2 is equal to 3 ohms. So two unknown resistors are there, R1 and R2. When it is balanced, option B, R1 is 6 ohms and R2 is 15 ohms. Third one, R1 is equal to 1.5 ohms and R2 is equal to any value. R1 is equal to 3 ohms and R2 is equal to any value, right? So we have to find the values of R1 and R2, but this is one Wheatstone bridge arrangement. This is one Wheatstone bridge arrangement. This is the center arm because the voltage is connected, the external battery is connected between A and C. So the B and D are the center arm. We must have the VB and VD as same because it is Wheatstone bridge. Already it is given. It is Wheatstone bridge arrangement. So no matter how many resistors are given here, right? So this is the center branch. Usually we will have one galvanometer there. Otherwise the resistance of the galvanometer will be given. Otherwise a specific value other than the galvanometer value will be given. One particular resistance value will be given additionally, but here 1, 2, 3, 4. 4 more resistors have been connected, right? But if you look at it, this can be simplified. This arrangement can be simplified because 3 plus 2 in series, R2 plus 30, this is in series, and this 2 ohms, this is in parallel. So these two are in series, these two are in series, 1, 2, 3. 3 such parallel arrangements are there. Yes. This is series and this is series. All the 3 branches are coming in parallel. So I can make this part as a single resistance. I can make this center part as a single resistance, right? Let me redraw it. This is 10 ohms, 30 ohms. This is the center part. I am writing it as Rx because I don't know the value of this. If R2 is known, only R2 is known, we can write the value of this Rx. So this is R1 and this is 9 ohms. This is the setup. If R2 is known, I can write the value. So time being, I am writing Rx. Since it is a Wheatstone bridge, to obtain balancing, we must have the condition 10 by 30 is equal to R1 by 9. 10 by 30 is equal to R by 9, or 1 by 3 is equal to R1 by 9. So R1 is equal to, from here I can write R1 is equal to 3 ohms. If R1 is equal to 3 ohms, then this bridge is a balanced bridge. So Rx value, it is no matter this Rx value is of any value. If it is 3 ohms, it will be a balanced one. The Rx can be of any value. So R2 can be of any value. But the condition is R1 must be 3 ohms. R1 must be 3 ohms. R2 can be any value. This is also true. R1 is equal to 1.5 ohms. R1 is equal to 6 ohms. Here R1 is equal to 3 ohms. R2 is equal to any value. This is the most appropriate answer. R1 is equal to 3 ohms, R2 is equal to 3 ohms. This is also true. But here R1 is equal to 3 ohms, R2 is equal to of any value. If it is any value, you won't have any current through the center branch, right? So this is the correct answer. Option D. So last problem. Find the equivalent resistance between the points A and B. Find the equivalent resistance between the points A and B. I have brought this problem here to solve by using Wheatstone Bridge method. By the same problem, but the same problem can also be solved by mirror symmetry, as I told earlier, and folding symmetry. Both the methods are possible. If you place a mirror here, it is mirror symmetry. If you place a folding axis here, it will be a folding symmetry. These two methods are also possible. Already I told you, you can watch my video under the heading methods of symmetry. The video link is given in the description box. But here we are going to solve the same problem using the Wheatstone Bridge arrangement, right? It is extended Wheatstone Bridge. 2R, R, 2R, R. You forget about this part. For time being, you forget about this part. This is A and this is B, right? This is A and this is B, the same line. So 2R by R is equal to 2R by R, balance. So this can be removed, balanced Wheatstone, right? Then you come here. If you come here, the bottom part, again you can ascertain that this is also a Wheatstone bridge, balanced Wheatstone bridge, right? Extended Wheatstone bridge, it is known as. This can also be removed, the center part. Now 2R in series, R plus R, because it is in series, 2R. Then the 3 are in parallel. 1 by RAB, 1 by 4R plus 1 by 2R plus 1 by 4R. LCM 4R, the small r. 4R is available. So this is R plus 2R plus R. So this will be 2R plus 2R divided by 4RR. 1, 2 I can remove. So R plus R divided by 2 RR. This is 1 by RAB. So RAB is equal to 2R small r divided by R plus small r. 2R divided by R plus small r. Option B is correct answer. 2 capital R small r divided by R plus R. Right? Guys, this is the end of this video lecture. As I told, mirror symmetry is also possible for this problem. Folding symmetry is also possible for this problem. Already we had one problem where mirror symmetry is possible in that problem. Folding symmetry is not possible in that problem. Where is it? Yes, this one. Folding symmetry is not possible problem. To have some idea about mirror symmetry and folding symmetry, you go and watch that video also. Wheatstone bridge is a simple arrangement, easy problem to solve. Only thing is you have to identify whether the Wheatstone bridge setup is available or not. That's all. Thank you for watching. Good luck.